So 6.2, the rest of it is much easier than the cross section. Okay, basically you're using density formulas and average value formulas tomorrow. So if you guys know what density is, right?
Yeah. The concentration of matter in whatever area.
Density is mass divided by volume.
Yeah.
Pounds per cubic foot. Oh, well, yeah, we deal with the other one every day here, but you can also write it if you have a rod. Density is mass divided by length. So the key here is that total mass for us, okay, would be linear mass density times length. That should have two S's. Yeah. So how dense is a rod per foot times length? Okay. We can use calculus to calculate the total mass. Okay. So so I'm the world's worst teacher because I fail to control my calculus class on a daily basis.
I was wondering if Tanner was wondering.
Yeah, he could actually join us live and ask questions and everything.
Yeah, Tanner is texting that.
Cool.
How do they measure the density of ship? I want to see the space on the side.
Displacement of water is based completely on the mass of the ship.
Tanner.
Yep.
Hi, buddy.
Basically, the ship goes in the water, and when it's displaced the same amount of water as its mass, it floats. If it doesn't, it sinks. Yes, that's a great question. Here's just a little fun fact for you. In Germany, you know what? I'm going to see if I can find a picture. This is a good exercise in mass.
There was a project to build aircraft carriers out of ice.
Okay, just an aside. They built a canal in Germany that has to cross this river. Okay?
Whoa, that's cool.
The question is,
That's a river.
what's the difference between the static load of the bridge with just water and the dynamic load of the bridge with the ship in the water? What's the difference in the amount of weight that the bridge has to hold? Anybody?
Wait, ask questions.
What's the difference in weight that the bridge has to hold with just water and with a ship and the water? The difference is 0. Because the ship's mass displaces the same amount of weight of water off of the bridge. There's no more weight on the bridge. Yeah. So little fluid dynamics is pretty cool stuff. Yeah. So thank you, John Riley, for making that an interesting tangent. Yes. It is pretty cool. So back to density. So if we're gonna do, is he online?
Oh my God, Tanner!
All right.
Get Tanner's face on that screen.
No. Okay. So if we want to do this, in calculus speak, somebody's having fun. Okay, the P of X, so obviously the rod is from A to B. It's some length, right? That's our integral. This function is what is key. Because the rod, you know, a lot of steel rods are the same density across the whole length of the rod. But you can build a rod that's maybe this dense and it gets more dense, but then it comes down. Okay, and we can model that with a function. So we can actually find the total weight of mass of the rod with calculus. Lo and behold, it's just the area under the curve, right? So
Area between two curves, is that kind of what we're doing here? We're finding the area from the top of that rod to the bottom of it.
just how much does, what's the mass of the rod, basically? Okay, so let's say we have a 2-meter rod. The density is 1 plus x times 2 minus x kilograms per meter.
Oh my goodness.
We'll watch it if you guys behave.
Allie, you want to watch the video? No.
Okay. So set up the integral from, okay, 0 to 2, and P of X is, you just set up your total mass calculation. Okay. I encourage you to do what? Yeah, distribute.
X distance from the rod and where the rod is.
X is the distance from one end of the rod. So it's
To where? The width of it?
length. It's length. Yeah, but you don't know what the density is at each length. Right, so at 1 meter, the mass might be different, or the density might be different than at 1.5 meters. So that's why we have to qualify that. Okay. Now if you work it out, you get your Are we okay with that?
Yes.
So basically, it's just a formula. Be able to use it. Okay? That's linear density. Okay, here's another one with radial density. You guys ever watched the show where there's like this fake nuclear blast and it killed a bunch of people?
Yeah.
Or there was going to be a fake nuclear blast and they estimated how many people would die
Oh, yeah.
based on population density?
Yeah.
Yeah, they use calculus. This is what it is. Okay? So you can calculate the population.
Wait, then what was the last density we just did?
That was linear.
Linear density.
Yes. So if we have like Denver, right? Denver's made in pretty much concentric circles the further you go out. You know the radius and the population density. Okay, the density function is P of R.
That's about the same here.
What?
Is that over on? Yeah, R?
This is an R.
Okay.
No.
It's the interval. Yeah.
Zero to big R.
Okay. Big R.
No, it's
Yeah, the Google Classroom. It's a discussion.
yeah, technically you could do one. Then you ask questions next week. Better than this.
What?
So,
Tanner, when you should get some rest, bud.
What's wrong with
Tanner, they're talking trash.
what's in your house?
I'll let you beat them up tomorrow. Okay, so here's an example. In your book, it says some certain city has a radial density function Oh gosh. Okay, R is the distance from city center. Basically, this is a play on the pi r squared, area of a circle. So, okay. How many people live from 10 to 30 kilometers from city center? Well, that sounded great.
Wait, Mr. If you're actually doing this with an atomic bomb, does it take into account the people that would just die instantly?
That's another part of the equation.
Then what about the people that love that radiation?
That wave when it goes out.
The function, yeah, there are a few ways to do that one. We'll just avoid it for now because we're at a very basic level. Basically, you're going to have an effective kill radius, and it's going to decrease from there. Okay, so this is what we're looking at, right? What's the integral? What are the limits?
10, 30.
The function, okay, don't forget the R. There's an R out front, and then the function. This one's kind of messy, that's why I wanted to do it. So. Oh, I forgot something. Yep. Bam. 2 pi up front. It's part of the formula. It's it has to do with circles, you know. Okay. Let's constant. I'm going to bring it out front and rewrite this to be a little bit more visually friendly. It helps you see what you need to do easier. Yep.
Oh my god.
We're practicing our use substitution here. Yes.
And we're gonna use 1 plus r squared. Is that correct? So,
Okay, what is u equal to? Yeah, we could do that. So du is? Okay, so we have square root of u, and r dr is replaced, but we have to put this over 2 because it's 1/2. So the 1/2 goes here. Du is replacing r dr. Now, what are my new limits? Yeah. 10 squared plus 1. 930 squared plus 1. Okay, so we have 15 pi from 101 to 901, u to the negative 1/2. That 1/2? Yeah. Yeah, so do your integral. So it's add 1, divide by 1/2, right? Divide by 1/2 is the same as multiplying by 2. So they're about almost 1.2 million, or 2 million people in that.
and you gotta plug that u back in. Or do you?
No, we completely changed this to u sub in terms of u because we changed the integral limits. Okay. Integral limits. Yeah. Okay, there is one more dealing with flow rate. An example 6 is actually dealing with flow rate in blood vessels, future positions. Okay. Not going to go over it in the interest of time. It's the same deal as the rest of them. You might not. You just have to go by the situation. So it's pretty much the same formula as this one because it's circular. Pipes and blood vessels, it's just adapted to flow rate. What is flow rate? It's a unit of volume per time.
That's the first question.
Volume per unit of time, so 10 gallons per minute. The river flows at 10 cubic feet per second. It's volume of something over time.
That's the first question on the homework. What is it?
All right. Do you have it written down already?
Anybody need it written down again?
What the heck was that?
Just in case.
Oh, yeah. I don't recall. Of course you do.
And
you're.
C also did Friday.
Yes. So I'll do Friday.